Dr. V. Jayalakshmi, is working as a professor in the Department of ECE, Anna University, Chennai. She has more than 17 years of experience in teaching. She has published more than 90 papers in international and national journals and conferences. She has organized more than 10 workshops and has attended more than 40 workshops and seminars. She has guided more than 100 projects in both UG and PG level. She is supervising 14 research scholars. She has established an AICTE-sponsored MODROB project for VLSI Lab. She has an endowment award for the top rank holder in PG degree and has 4 cash awards for producing 10% of result in Anna University curriculum. She is a life member in various professional bodies like ISTE and IETE. She has specialized in mobile communication, microprocessor and microcontroller, digital system, computer networking, and neural networks.
Welcome to UGC lecture series. In today's session, we will discuss about timing diagram and input interfacing. Timing diagram for out instruction and how to interface the input devices with the processor will be discussed on today's session. So, in the timing diagram, first we have to know how to draw the timing diagram. So, and what are the elements are required for the timing diagrams. So, timing diagram is a waveform representation which is used to calculate the execution time. So, in the timing diagram consists of 3 important terms, which is instruction cycle, mission cycle and T states. The instruction cycle is the time required to calculate the one instruction. Mission cycle is the time required to complete the one operation. The T state is defined as the one subdivision of the operations. So, the mission cycles consist number of T states, the instruction cycles consist number of mission cycles. So, based on the number of T states we have to calculate, then we have to draw the timing diagram. So, for the in instruction already we have discussed how to draw the timing diagram for the in instruction. Today we will discuss with the example. So, what is the format for in instruction? So, in instruction is in 36H. So, it represents 36 is the port address, in is the opcode. So, in opcode the opcode value is dB. So, 36. So, when we are executing this instruction, how many addresses required? So, totally 2 addresses required. That address is loaded in the program counter. Suppose you are taking the address 4500. So, in the 4500 first the opcode dB will be written. Then the next consecutive address 4501 we are taking as the data 36. So, during the program execution, this first one is represented as a opcode fetch cycle. So, fetch the instruction which are already stored in the memory. Next instruction is 36, which is the operand. Here we are performing the memory read operation. So, it read the data from the memory. So, these two is a 2 byte instruction, but actually one more term is required based on its operation. Now, only we are transferring by using the in instruction, what it explained, from the 36 the content is moved to the accumulator to the A register. Now, we are loading only the opcode, then we are loading the operand. When we have to transfer the data, now we have to load the address 36, the content of the 36 is loaded into the 36. So, what is the content? Suppose if we are assuming the content is 20. So, now in the third cycle, now the 20 is moved to the 36, that is the instruction execution. So, for this how many mission cycles are required is the M1, M2, M3, 3 mission cycles are required. This full is called as the instruction cycle. The instruction cycle having a 3 mission cycles M1, M2 and M3. M1 is the opcode fetch, M2 is operand, M3 is the internal operation. Here what type of operation is performed means we are reading the data from the peripheral device. So, IOR. So, these 3 are the very important term. After knowing this, we can start to draw the diagram. So, to draw the diagram, what are the terms we have to give in the timing diagram? First, we have to draw the clock pulses. Based on the number of mission cycles, we have to divide it as number of T states, then we have to draw the clock pulses. Then we have to specify the address. So, here the address, higher order address you can directly give, lower order address which are multiplexed with the data. So, you could not give it directly. So, you have to first give a small circle for address, then you have to give the data. So, how we are separating this address and data means with the help of ALE signal. So, first you draw the higher order address, then multiplexed address and data, then third one is ALE. So, after enabling this, now we have to think of which operation is performing, either read operation or write operation. And that read and write is performed with either memory or peripheral devices. So, based on that we have to give the number of lines for representing. So, this is a timing diagram for the in instruction. This is a M1 mission cycle, this is a M2 mission cycle, this is a M3, this is a complete instruction cycle for the in instruction. So, this is a M1 mission cycle, M2 mission cycle and M3 mission cycle. So, the M1 mission cycle consists of 4 T states. So, 4 clock pulses are applied, then M2 and M3 consists only the 3 mission cycles. So, the address lines, first we have to draw the higher order address lines A15 to A8. So, this is till T3 we are connecting, the T4 state is unspecified which represents the address is already read, then 3 T states which is used to read the addresses. Then multiplexed address and data lines, in the T2 state we have drawn only the address, part of T2 to T3 we have drawn the data lines. This is repeated for all mission cycles. The ALE signal which is a address latch enable, based on the name it will latch only the address. When the latch is enabled it will hold the address. So, during the first T state of all mission cycles it is high. So, it will read the address on this cycle. Then to represent either we are performing the operations with IO devices or with the memory, this signal will be useful. IO/memory bar. When the signal is high, it represents it's a peripheral related operations. When the signal is low, it represents the memory related operations. So, for the mission cycle 1 and 2, it have memory read operations. So, we are putting the low signal on the first 2 mission cycles. Then third one is actual the performance of the reading operations from the peripheral device. So, we are giving the high signal on the M3 cycles. Then read bar signal is always low part of T2 to part of T3 in all mission cycles, because that time only we are loading the data. Then based on these 2 signals, memory read bar and IO read bar signals are placed. So, based on the previous example, now we will write 4500. Where to write the 4500 means this is divided as lower order address, higher order address. So, the lower order address should be written in the A0 to A7 and the higher order address should be written in the A8 to A15. So, here we have to write as a 45, here we have to write it as a 00. So, first we are placing the first address which is in the program counter, then we have to give the corresponding opcode which is DB. The next consecutive instruction will be read in the machine 2 cycle. So, here 4500 01. The next consecutive address. In this consecutive address, we have to write the previous address which is a 36. So, here you can write it as a 36. So, now we have placed these 2 with the help of ALE, with the help of memory read we are reading these 2 data. In the third mission cycle only we are reading the data from the mission cycle from the input device. So, here we have to place the port address. What is the port address in 36? So, the 36 is the port address. So, here we are writing the 36 in both lower order address and higher order addresses, because it will read any one of the data. Then what we have assumed as a input, we have assumed the data as a 20. We have to write the data 20. So, based on these 3 mission cycles, first mission cycle it will read the opcode by using the 4500 address. The next 4501 will read the data operand of or port address of 36. In the third mission cycle, the port address is placed, then it will read the data 20. At the end of T3 only, the data which is available on the input device is transferred to the accumulator of the corresponding device. So, this is the in instruction execution, and based on this you can calculate the execution time also. Next we will discuss the out instruction. In the out instruction, this is a whatever we have the data in the peripheral device, it will be transferred to the display device, either as to the monitor or to the printer. So, how we are transferring? To transfer the data available on the processor to the output device, we have to know the port address. So, after calculating or after identifying the port address, we have to know which data to be transferred. So, via the data lines or via the accumulator, we are transferring the data to the port address. So, we are sending the data from the processor to the peripheral device. So, for this operation, we need the write operation. The out instruction is performed with the write operation. This is a format of out instruction, out 75H. Actually, out port address we have to give. So, here we are considering the port address 75H. The IO instructions are performed with the 8-bit address lines. So, among this 8-bit we can use 00 to FFH. So, from this address you can take any one of the address. Here we are considering the 75H. H represents the hexadecimal number. So, during the execution, how we are typing the instructions? 4500 we will write the opcode of the out instruction. Opcode of out instruction is D3. Then the next mnemonic is 75, which will be written on the next consecutive address 05. So, based on its internal operations, we are taking the third one. So, the third one is the actual operation in the out. So, what we are doing? From the accumulated data is transferred to the specified address. So, we are assuming the accumulated data is 30. So, the 30 is transferred to the 75H. So, how many machine cycles required for this? 3 machine cycles are required to execute this out instruction. Actually, the out instruction is a 2-byte instruction. Based on its operation, it have a 3 machine cycles. The first machine cycle is a opcode fetch cycle, second one is memory read cycle, third one is IO write cycle. So, this is a 2-byte instruction. To execute this instruction, we need the 3 machine cycles. So, first machine cycle is opcode fetch cycle, which have a opcode as D3. The second machine cycle is memory read operation. Third one is the IO write operation, because we are sending the data to the peripheral. So, we have to use the write operation. So, how to draw the timing diagram for the out instruction? So, in the out instruction, what are the data we need? First, we have to draw the address line, then multiplexed data lines, then the control signal, which is to enable the address latch. Then the control signals remaining, what type of operations we are performing, read bar or write bar, along with that either IO memory bar. The bar represents this is the active low signal. Active low signal and active high signals generally we are using, because these are the binary terms, that is active low means it is activated by applying the 0 volts. Active high means it will be applied by the 1. 1 represents plus 5 volts. VCC and ground we are using. So, 0 volts when we are applying, the active low signal will be enabled. When we are applying the high volts, that is plus 5 volts, automatically the active high signal will be enabled. So, based on these signals we are performing, then it has the out instruction out 75H. So, in the out 75H, this is the opcode, which is a D3, this is a 75. Suppose I am taking 2040 as a program counter address. So, the program counter address 2040. So, first we have to write the D3, then the next consecutive address 2041, which is a 75, the operand we have written. So, when we are writing any instructions, only the 2 address will be useful, but based on its internal operations, the third cycle will represents the operation of the cycle. So, here we are giving the 75. So, what is the meaning of out 75H means? So, the accumulator content whatever it may be is transferred to the port address 75. So, we are giving the value. So, then third one we have to specify the port address. From this the data, suppose we are assuming as 30, the 30 will be transferred to the given address. This is the timing diagram for the out instruction. So, this is a M1 which is opcode fetch, this is a M2 memory read, this is a IO write operation is performed, this is the opcode fetch. So, this consists of 4 T states. Here we have to write the address what we have considered in the previous example. This is a higher order 20, lower order is 40. The corresponding opcode is D3. In the next addresses, which is the memory read, to read the port address. So, 2041. So, we assume the address as 75. So, based on this, the ALE is used for demultiplexing, read bar and write bar signal automatically enabled with the IO memory bar signals. In the third machine cycles, we have to give the port address 75, 75. We have assumed the data as 30. Now, the accumulator value 30 will be loaded onto the 75 port address at the end of the T3 cycle. So, the T3 cycle, the M3 cycle will define the operation of the IO address. Now, we will discuss the execution time. So, when we know the execution time, we can efficiently run any one of the program. So, for calculating the execution time, we have studied the timing diagram. So, based on the timing diagram, we have to identify how many T states required for each instruction. So, to calculate the execution time, we have to first determine the number of T states. Then we have to know the internal clock frequency. Based on the internal clock frequency, you can calculate the time. So, the execution time is nothing but the number of T states into internal frequency or internal time. For microprocessor 8085, the frequency is 3 megahertz. 1 by f is 0.33 microseconds. Suppose we are taking the out instruction, out 75H. In the first mission cycle, which is opcode fetch, we have 4 T states. So, 4 into 0.33, we can calculate the execution time for the opcode fetching. In M2, 3 T states. So, 3 into the corresponding time 33 microseconds. For M3, which is IO read, we are calculating 3 into 0.33 microseconds. Suppose you want to know the execution time for all instructions, simply you can add it. So, totally 10 T states. So, 10 into 0.33 microseconds. So, based on that, I think you can know how to calculate the execution time. Now, we will discuss the peripheral interfacing, how to interface the peripheral devices with the microprocessor, and now we will discuss only on the input device, how to get the data from the keyboard or mouse or from the any one of the switches. So, before that we will discuss what is the need of interfacing. So, interfacing is nothing but the data transfer between the processor and the peripheral devices. It is used to communicate with the external world. Via the accumulator only you can perform with the external world. It interconnect the hardware and software, and this is used for the real time application and automations. To interfacing the microprocessor with the peripheral devices, we have addresses 00 to FFH. From this address you can select any one of the address. This diagram shows the simple IO interfacing with the microprocessor. So, for interfacing with the microprocessor, so how many data are required for this means, first we have to select the address and data. So, the higher address, which is A8 to A15, you can directly connect it to the IO devices. For any interfacing, you have to draw the 2 boxes, then you have to give the what are the required signals or what operations we are giving. So, we are giving the address and data lines. So, the higher address A8 to A15 is directly connected, but the remaining address A0 to A7 you couldn't directly connect, because these are the multiplexed address and data lines. So, we are connecting via the latch. 74373 is a latch. This is the octal latch. Via the latch we are connecting. So, when the latch is enabled, it will give only the address line A0 to A7. Otherwise, it give the data lines D0 to D7. So, when the latch is enabled means by activating the ALE signal. When the ALE signal is high, the latch will be enabled, then it will give only the address lines. So, from the IO device, we are performing only 2 operations, which are read and write operations. So, read operation means we are getting the data from input devices to the processor. So, we are giving this direction. Out means we are sending the data from the processor to the IO device. So, we are sending the direction as write bar signals. So, whatever it may be, we have to select the CS, that is chip select. After activating this signal CS bar, then you can perform either read or write operations after sending the address and data. This is a simple representation of input interfacing, how the processor read the data from the input device. This is the input device, we may connect either the keyboard or from the switch or from the mouse. Whatever the data is detected, that will be sent to the D0 to D7, it will pass to the processor via the port. So, for interfacing, what are the signals are required means, already we have discussed address lines, data lines, along with which operations we are performing. Read operation means we have to select the RD bar signal as RD bar or RD signal as low, then IO memory bar signal. Bar indicates which is a active low signal. So, when we are selecting the input device or output devices means by selecting some control signals. This is a 3×8 decoder. So, this is a device selection, how to select the IO device. Here we are selecting the decoder will decode to select any one of the particular address. We have a 8 address line which is A0 to A7. So, 8 inputs we are given to the decoder, it will select 8 to 256 address lines. So, here the address is 00H to FFH, we can select any one of the addresses. So, the decoder will select any one of the address, that address will be combined with the control signal, which operations we are performing, either read operation or write operation. These two signals are combined, then only it will give the device select signal. This device select signal will be used as a enable of the latch. Once the latch is enabled, the data available on this will be transfer. This is the in instruction. So, from this input peripheral device to data, this data signal is passed to the microprocessor. This is a device selection. Device selection is depends on the IO address and some control signals. So, the address lines are decoded to generate the signal that is active when the particular port is being accessed. Then IO read bar signal is generated by the combination of IO memory bar signal and read bar signal. This is the interfacing of switches. So, how to interface or how we are reading the data from the switch. Here we are considering the 8 switches S0 to S7 which are connected to the buffer via the pull up register. Then these data lines are connected to the microprocessor, it have the decoder which is used to select the decoder line. So, to interface with the DIP switches, decoder with IO select lines, buffer and switches are required. So, this is a 3 to 8 decoder. So, in 3 to 8 decoder means 3 input lines, it will give the 8 output lines. So, among the 3 based on our input signals we can select any one, 3 enable signals. These 2 are active low signals, 2 active low signals. So, we are connected with the inverter. So, the outputs O0 to O7, 8 outputs are available. So, this is a 3 to 8 decoder. So, we have given this. So, from this we are selecting the 4th output. So, when you want to select the 4th output, we have to give the signal as 1 0 0. Then these 2 are active low signals. So, we have to give a 1 1, then automatically these 2 will be 0, this is a 1. So, based on this we have to identify the address lines. Then this is a IO read memory bar signal. When the signal is high, then it indicates the IO operations. When the signal is low, it is a read operation. Based on this we are selecting this. So, these 2 signals are now low signal, this low signal is given, this is also low signal, then again inverter. So, we get the IO select bar signals. This signal is used to enable the buffer. Once the buffer is enabled, then it automatically read the data from the switches. So, 8 switches which is connected to the VCC. So, when the signal is open means it represent as a 1, when the signal is closed means we read it as a 0. So, based on that we can send any data. Suppose these 2 switches are closed means only these 2 values S3 and S4 will be 0, remaining signals are high. So, based on that we can read the data. This is the decode logic for how to detect the DIP switches. The same thing here we have a 8 address lines. Among the 8 address line we can select any one of the address, that address is combined with the NAND gate. Another input is we are getting from the control signal IO/memory bar. These 2 signals, when the signal is 1, this signal is 0, then the output is 0. Then it select the IO read bar, then 0 0, this is a 1, this is active low signal. So, 1 it send the signal as 0 signal. So, active low signals we get, this is used to enable the buffer. So, whatever we are detected from the switch, it simply passed to the microprocessor. So, to read the IO devices we need some steps. First we have to decode the address from the by the decoder. That decoded address is given to the AND gate along with the read bar signals. These 2 signals are combined and generate the device select. This is one of the diagram which is for input and output devices. This is a decoder, 3 to 8 decoder, 3 inputs we are giving, the unused address lines are connected to the enable signals. So, from this we have selected the 2 addresses, one is for output, another one for input. So, the input for this remaining signals are high signals. So, here we are giving 1 0 0, then it will select F8, 1 0 1 means it will select the FA. After selecting the FA, that is we have to give a 1 1 1 signals for all values. Here is we are selecting 0 1 0. So, actually what is the signal 1 1 1, then 1 0 1 0. So, this is F, this is A. So, here we are giving the FAH. So, then by the FAH we are reading the data. So, the read bar signal is activated, then it will select. So, whatever the switches are closed and open, based on that the ones and zeros are read and transfer to the processor via the data lines. The another address is F8. So, for F8 we are considering this as 0 0. So, automatically 1 0 0 0, this is the same thing. So, F8H we are detected. So, via the read write operations, these two select the latch. After enabling the latch, whatever data available on the accumulator will be transferred to the LED. So, suppose we have signals 1 0 1 0 1 0 1 0 means the corresponding alternate LEDs will be on and off. So, in the today's session what we have discussed, how to draw the timing diagram for in and out instructions and how many machine cycles required for each instruction. Based on that we have to calculate the execution time. Then what is the difference between the in and out instruction? Mainly the in and out instructions differs based on the read bar and write bar signals. If the data is available on the data bus, based on either read means we are sending the data or receiving the data. Based on that the directions only varied. Then how to interface the input devices? We are connecting the input devices either keyboard or mouse or the switches. Based on the on and off or based on the corresponding row column address, we are detecting the particular key which is already stored in the microprocessor. So, based on today's session, we will just recollect a few points. Can you define what is the length of port address? Can you define the memory capacity of peripheral device? How many T states in the in instruction? What is the execution time for out instruction? Which signal is used to enable the latch? Thank you.